is Ross Grassie. I'm a senior researcher at the University of Edinburgh and the technical program manager at the Quantum Software Lab. I'd like to start today by thanking the conference organizers and the British Embassy for giving me the opportunity to speak about our mission, our methodology, and to show some of the expertise that we have at the Quantum Software Lab. Our mission is to accelerate the search for useful quantum applications. Now, there are two criteria that need to be met in order for us to consider a quantum application useful. So the first one is it must be used in the real world. It must be interesting to industry or government for whatever their needs require. And second, there must be the potential to see a quantum advantage for this particular application. There must be a reason that you want to choose a quantum solution over the classical counterpart. Our method for achieving this goal is to employ a startup culture within our academic institute. This means that our academics are pooling their resources and aligning their research expertise in order to meet the needs of our industry collaborators. Through workshops and discussions, we are identifying industry pain points. We are developing use cases with them. We're then translating their needs into mathematical problems that we can give to our researchers. And then the researchers are designing, implementing, and benchmarking these quantum applications against other quantum solutions and also against the best-in-class classical solutions. And it's incredibly important that the output from our benchmarking is going back in so that in future we can design and implement better solutions. And we will continue to keep on going round this cycle until we have got the best out of the quantum technology and we can output some kind of product at the end. So for us, because we're an academic institute, our products are maybe a little bit different. We're looking at open source software, software development kits, feasibility studies, papers, and these sorts of things. When we're thinking about quantum advantage, there are three questions we want to answer. If quantum advantage can be achieved now, what platform is it on? What software is it using? If it can only be achieved in future, then what needs to happen now so that we can actually get there? Is it more qubits? Is it better fidelity? Is it better networking? Is it HPC integration? We want to know what that is. And also, if it can't be achieved, what is the actual underlying reason why we should really stop looking at this application? So now I've got a couple of examples of our methodology working in practice. So the first one comes from security, and we're looking at device authentication using a piece of technology we developed called the quantum lock. And that was undertaken by these fantastic researchers here who are based both at the University of Edinburgh and at Sorbonne University in Paris. So through discussions with security companies, we found that they were particularly interested in using hardware security for device authentication. In particular, they wanted to use physical unclonable functions, or PUFs. Now, the classical solution is the pain point for the classical solution is that there is insufficient randomness in these PUFs. If an adversary is able to gather enough of the keys that are output by these PUFs, then it can use a sophisticated machine learning attack in order to learn what future keys will look like and break our authentication protocol. So we wanted to ask, can we introduce some quantum randomness on top of this classical randomness and create a quantized PUF that will perform better? So our framework for this is the adversary model. That's how we're going to compare our classical and quantum solutions against one another. We really want to improve the security of this protocol. In particular, we want to see what the forging probability is. Can our quantized PUF lower the probability that our adversary is going to forge our puff and break our protocol. So our first attempt was a fully quantum solution. So although it was able to lower the forging probability and perform better than the classical solution, the infrastructure assumptions were far too strong. It required quantum memory and hard random state generation, which just isn't possible right now. So there was a bit of work that needed to be done in order to improve this. However, at least we were able to see that the forging probability was lower, and there was some reason for continuing to use this application. So yes, we went back to the drawing board to see what we could do the second time around. Our second attempt was a hybrid puff. So this reduced the requirement on the infrastructure. However, it was only secure against weak adversaries. A fully fault-tolerant quantum adversary would still be able to break this particular protocol. So back to the design stage once again. And on our third attempt, we combined the hybrid puff with the classical state-of-the-art, which is called the lockdown technique, to create the hybrid locked puff. Now, this is strong against any quantum adversary, and it has the improved infrastructure requirements of our second attempt. To benchmark these different puff solutions, we ran some simulations, and we have the classical puff here in blue on these graphs, the hybrid puff in red, and our third attempt, our best attempt, in green. So going along the x-axis here, this is the amount of data that is required before an adversary will be able to break our authentication protocol. And this is showing the forging probability. So once this forging probability hits 1, it means that definitely an adversary has been able to break our authentication protocol. And in each of these scenarios, we can see that the amount of data that is required before the forging probability hits 1 is the worst in the classical case. So the classical case is performing worse than our quantum solutions. Our second attempt performed a little bit better, and our third attempt was the best so far. So to summarize, we found that there was insufficient randomness in the classical solution by talking with companies to see what they were interested in. We asked whether we could supplement the classical randomness with quantum randomness to create a quantized puff, and asked whether that would be able to lower this forging probability. This led to the design of this hybrid locked puff, which was able to do that, but importantly, only in simulation so far. So a clear next step is to reduce the infrastructure assumptions even further so that this can actually be implemented on the QKD technology that we have today. And there is a paper coming out soon which shows exactly this. We would also like to be able to demonstrate this hybrid locked puff technology on real devices, and we do have an industry collaboration in place so that we can do just that. So for those who are interested in the rest of the technical details for this project, if you scan this QR code, it will take you to the paper and you can read more. So our second example comes from the energy sector. So this was work done in the engineering department at the University of Edinburgh and conducted by Thomas Morstan, one of our lecturers. So this project started through discussions with the National Grid, who run the electricity distribution network in the UK. And we were told that as more and more renewable energy sources are getting added into the grid, it's becoming very difficult to predict how much power needs to be generated by each of our power stations. With each addition of a renewable energy source, it's introducing more decision variables, and for the underlying mathematical problem, that increases the number of decision variables, and the classical computational complexity scales exponentially with these decisions. So we want to see whether a quantum annealing solution would provide better scalability so that we can find out how much power we should be producing. The framework, in this case, is a combinatorial optimization problem, and as such, we have a cost function that we want to minimize. So really, what we're asking is, can we still get a good solution, but at scale? To do this, we formulated the problem as a quadratic, unconstrained binary optimization. We used D-Wave's advantage processor and adiabatic quantum computing in order to find our solution. So good news, we did manage to find that the number of qubits scaled linearly rather than exponentially in the decision variables. Bad news is that the quantum solution wasn't actually as good as the classical solution. And in fact, as the problem size grew, then the quantum solution continued to get worse. So there's definitely some work to do. So to summarize, we found that there was poor scalability in this optimal power flow problem, at least the classical solution. We then wanted to see whether a quantum annealing solution would be able to provide a good solution, but at scale. So we implemented it as a QUBO problem on D-Wave, and we did find better scalability. However, our solution was worse. So clear next steps are to maybe try some alternative hardware, alternative problem formulations, and then compare and contrast across different hardwares. So to this end, we are in the process of getting access to various hardware platforms, and we are also hiring some researchers in order to formulate this problem better. Additionally, we'd like to apply the lessons learned from this to similar problems from the energy sector, such as unit commitment. And again, these researchers that we're hiring will likely work on these. So again, if you're interested, please scan the QR code, and that will take you to the technical paper for the details. So these were just two examples of some of the projects that we're running at the Quantum Software Lab. We have teams working in quantum machine learning, benchmarking, verification, quantum error mitigation, and simulation as well. At the University of Edinburgh, we're not only talking to ourselves, we're talking to the School of Computer Science, the School of Physics, School of Chemistry, Engineering, and that's so that we're not just bringing the best quantum expertise, we're also knowing what the best classical state-of-the-art solutions are as well. Through our partnership with the National Quantum Computing Centre, we are aligned with the UK's National Quantum Strategy. We're getting access to different hardware platforms, and we're helping them in their use case development as well. So we're here today because we would like to collaborate. If you're an end user, we would like to co-develop use cases and translate your needs into mathematical problems to give our researchers. If you're a quantum hardware or a quantum software company, we want to co-design, implement, and benchmark quantum solutions on your platform. And it's maybe important to point out at this stage that we are academics. We're not industry. We want to do all the fundamental research that underlies your work, and we want to be completely open about how we do this to create open source software that everybody can use. If you are interested in speaking with us, find me afterwards. My colleagues, Jim is at the back, and Craig is here as well. We'll be more than happy to have a chat, or alternatively, please email us at this address. We really believe that our methodology will be able to take the real-world use cases coming from the end users and glue them together with those applications that might be able to demonstrate quantum advantage by talking with these quantum experts in your companies and also our own academics as well. And we're going to help the whole ecosystem accelerate their search for useful quantum applications. So, thank you.